Hello, student. In this session, I am going to explain how the Fermi energy of a copper material is determined. So this is an experiment, a simple experiment that you can do in your laboratory without much need of equipments. So it's a very simple one. So the aim of this experiment is to determine the Fermi energy and some other electrical properties of the copper. The apparatus required for this experiment are we need a constant current power supply, a voltmeter, an ammeter, electric kettle, beaker of 200 ml, and a thermometer and a copper coil is needed. So these are the simple equipments needed to measure the Fermi energy of a copper. So just I will brief the theory of this, what it means, the Fermi energy means. So this Fermi energy is a concept in quantum mechanics usually referred to the energy difference between the highest and the lowest occupied single particle states in a quantum system of non-interacting fermions at absolute zero temperature. So in a Fermi gas, which is the gas full of fermions means they are the particles whose distribution is obeying the Fermi Dirac statistics. So that kind of particles are called as the fermions, and the gas of such particle is called as the Fermi gas. The meaning of Fermi gas means the gas which obeys the Fermi Dirac statistics. The lowest occupied state is taken to have zero kinetic energy, whereas in a metal, the lowest occupied state is typically taken to mean the bottom of the conduction band. So the term Fermi energy is often used to refer to a different yet closely related concept. So many times we say that Fermi level. So it is also called as the electrochemical potential. Sometimes we say that Fermi level, sometimes we say that Fermi energy. So there is a slight difference between these two, and they are figured out below like this. The Fermi energy is only defined at absolute zero, while the Fermi level is defined for any temperature. You can see this is the first difference between the Fermi energy and the Fermi level. So when you say that Fermi energy, it is always defined at absolute zero, whereas the Fermi level is defined for any temperature, because the position of the Fermi level depends upon the temperature, and as the temperature changes, the Fermi level also changes. So Fermi level means I can say that it is the highest occupied level is generally taken or called as the Fermi level. And the Fermi energy is energy difference usually corresponding to kinetic energy, whereas the Fermi level is a total energy level including kinetic energy and potential energy. So Fermi energy, why it refers to only the kinetic energy? Because the electrons present in the Fermi level, and it means the topmost level, are loosely bound to the atoms, so that in a solid like metal, they will be moving with a lot of kinetic energy. So there, so lot of velocity. So there, that is why their potential energy is least, and hence they will be having more kinetic energy. The Fermi energy can only be defined for non-interacting fermions, where the potential energy or band edge is static well defined, whereas the Fermi level remains well defined even in complex interacting systems at thermodynamic equilibrium. So Fermi energy is most of the time is defined for non-interacting fermions like gases. So in case of gases, the interaction between the atoms is at least one. We can't say zero, but it is at minimum level. So that kind of systems, in such cases, we can define the Fermi energy. But Fermi level comes in any interacting systems, like even in semiconductors, when we make a doping, we much talk about the Fermi levels because the Fermi levels shift according to the type of doping we are doing. So that is why the Fermi level refers to the interacting systems, but Fermi energy is always refers to the non-interaction systems. Since the Fermi level in a metal at absolute zero is the energy of the highest occupied single particle state, then the Fermi energy in a metal is the energy difference between the Fermi level and lowest occupied single particle state at a zero temperature. So that means below the Fermi level, one more level will be there. So lowest occupied single particle state. Lowest occupied single particle state means this is the bottommost level in the valency band. So the energy between this level and the Fermi level is gives the energy of the Fermi level. The Fermi energy of the copper is calculated using this formula. EF is equal to like this. This is we have to derive separately. It is root of rho A M upon L, where this rho is the density of the material under investigation. And in this case, we have taken copper as the material. And this A is the cross-sectional area of the wire. Since we have taken a wire, a coil made of copper wire. And M is the slope of a curve of resistance versus temperature. So, and this capital L is the length of the total wire present in the coil. So these derivations, if you want, you can study separately. And since it is a practical part, I am taking these equations directly. So this is the equation to calculate the Fermi energy. So density of the copper coil is 8930 kg per meter cube. And cross-sectional area of the copper wire changes according to what type of wire you are taking. And slope also depends upon the type of wire used. And capital L is the total length of the copper wire present in the coil. And what are the other parameters we can calculate here are the Fermi velocity Vf is calculated in this way. Vf is equal to square root of 2 Ef upon m. Ef is the Fermi energy and m is the slope. So this Fermi energy is in terms of joule, means we have to take the value. So here this 1.6 into 10 to the power minus 19 is divided. If it is not there, this EF will be in terms of joules. Once you are dividing that value by this 1.6 into 10 to the power minus 19, so that converts into electron volt. So this care you should take care of. And this equation gives the Fermi energy in terms of electron volt, since we have divided by this quantity. And Fermi velocity, to calculate the Fermi velocity, we have to take EF. not in terms of electron volt, in terms of joule we have to take. So divide that quantity by m, where the small m is this. Here the small m is the mass of the electron. The Fermi velocity you will get in meter per second. It's a standard unit. And what is this Fermi velocity? This is the velocity of the electrons when they are moving in a Fermi level. Very simple. So that velocity is called as the Fermi velocity. And Fermi temperature is also calculated here, which is given by Fermi temperature Tf is equal to Ef upon K, where Ef is the Fermi energy and this K is the Boltzmann constant. So here this quantity also we can calculate. So this is about theoretical aspects, and experimental arrangement is like this, very simple. So here uh, we are using a battery. It's called as a constant current source, means where the current is not going to change irrespective of the load. Is that kind of power supplies are called as the constant current sources. And here we have connected a milliammeter, and this is a resistance box, decade resistance box, and here voltmeter is there, and all these are connected in series, and these two, this combination is connected to this copper coil. This is a copper coil. So simply it is a copper wire. You can wound over any plastic pipe or any wooden thing, whatever it is, you can make it coil. So the two ends of the copper coils are directly comes to this voltmeter. So this voltmeter measures the voltage across this, and all other things are in series. And this is a beaker of nearly 200 ml, and you have to pour the water sufficiently until this copper coil is completely merged or immersed in the water. And a thermometer, we have to place a thermometer here to note down the temperature. And in this way, you can connect. And after that, what we are going to do here is that the water is heated in electric kettle to its boiling point. Once the water starts boiling, you have to pour into this beaker, and you have to switch on the power supply, and you have to remove some small you have to unplug some keys here to connect a small resistance. This resistance, this is needed to control the current. Small this resistance is needed to control the current, because the resistance of the copper coil is very less. So if it is not there, the battery maybe gets shorted. So that is the problem. So what are the observations you are doing to do here is that the length of the copper wire in the coil, you should know it. In our case, it is around 20 meter. And density of the copper wire is a standard quantity. It is 8930 kg per meter cube. And using the screw gauge, we have given the details how to measure the diameter of the copper wire. Using the screw gauge, we determine the diameter of the copper wire. Once you got the diameter of the copper wire, you divide it by 2, you will get the radius of the copper wire. And once you got the radius of the copper wire, you have to calculate the cross-section area of the wire. As you know, the formula is pi r square. To calculate the cross-section area of the copper wire is pi r square, where r is the radius of the coil. So in this way, all these observations are made. Observation table will be like this. Temperature in degree centigrade is noted down from the thermometer, and this temperature is converted into Kelvin here by adding 273. to every number. And at every temperature, we have to note down the voltage across the coil and current across the coil. And using the Ohm's law, we are calculating the resistance R is equal to V by I. So, this is a simple tabular column which should be used to note down the readings. So procedure, take a screw guys. The first step is to take the screw guys, check for its zero error. There may be positive error, negative error like that. Determine it, note down it. Then determine the diameter of the copper wire and then obtain the radius of the wire. Hence calculate the cross-section area of the wire. Next, pour water into the electrical kettle and wait for until it boils. So simultaneously, we have to start the electric kettle so that the water boils. Okay. Next, meanwhile, make the connections as shown in the diagram and keep the copper wire and the thermometer into the beaker. Unplug some small resistance, say 2 ohm in the resistance box. Make the power supply and be sure that the ammeter reading is within the scale. Okay. So that means not only 2 ohm, you look at the scale of the ammeter, the pointer should be within the scale. You should not go beyond the out of the scale. That is the point. Then pour the hot water into the beaker and immediately start noting down the temperature, voltage and the current in the ammeter. So the temperature suddenly falls, starts falling down, and for every fall of 5 degrees centigrade, we have to note down the current and voltages in the voltmeter and ammeter. Then in the last column, you calculate the resistance using Ohm's law, R is equal to V by I by taking the corresponding voltage and current values. Then plot a graph of resistance versus temperature in Kelvin, which is a straight line, and obtain the slope. Then calculate the Fermi energy, Fermi velocity, and Fermi temperature using the equations given one and above. So this is the graph, nature of the graph. It may not be so straight, but almost it will be a straight line. And take the temperature on x-axis and resistance on y-axis. And after plotting, draw a straight line. Then take the note down the slope of the line. So these are the results which are to be obtained from this experiment. And here I am giving some actual values which are from our laboratory where we have done this experiment. And the length of the copper wire was 20 meter. Density of the copper was this much, 8930. And diameter of the copper wire was 0.457 mm. Radius of the copper wire was 0.228 mm. And cross-section area of the wire was 0.163 × 10⁻⁶ meter square. And these are the readings from our experiment. So when the water was poured into the beaker, the initial temperature was 90 degree in the thermometer. So this temperature is converted into Kelvin and temperature falls down, and by fall of every 5 degrees centigrade, we have to note down the temperature like this. And these are the voltage readings. Voltage slightly decreases, you can see, and current slightly increases as they are inversely proportional to each other. And these are the resistance values. You can see here as the temperature goes down, the resistance slightly increases. So the metallic behavior of this copper wire is exhibited here because metals have a positive temperature coefficient. If the temperature increases, the resistance increases. If the temperature decreases, resistance should decrease. So here, as the temperature is decreasing slowly, gradually, the resistance is also slightly decreasing. So hence, verifying the positive temperature coefficient behavior of the copper. Then we have plotted those readings and it comes like this. Since I have plotted in Excel sheet, I would have been put a trend line. I forgotten. So you take this as almost all a straight line. And slope of this line is 0.002 ohm per Kelvin. Slope is noted down. And this slope and all other parameters are substituted into the equations 1, 2, and 3. I'll go back and I'll show you. So here are the equations 1, 2, and 3. This is the equation 1. Slope is the thing you have to substitute from the experiment. All other things are measured externally. So m, the small m is the slope. We have to substitute and calculate the Fermi energy. Then once you got the Fermi energy, you will calculate the Fermi velocity. And this m is not the slope. This is the mass of the electron. Be careful. And then calculate the Fermi temperature as EF by K. So these are the three formulas you should use to calculate the parameters of the copper. And we have done it. So our calculation shows that we obtained the Fermi energy EF is equal to 7.75 electron volt. The standard value of this Fermi energy is 7 electron volt. So this shows that our results are in good agreement with the reported values. And Fermi velocity comes around 1.65 in 10 power 6 meter per second. And Fermi temperature comes about 8.99 into 10 to the power 4 Kelvin. So this is the simple experiment you can do in your laboratory to determine the Fermi energy, Fermi velocity, and Fermi temperature of the copper wire. So it is a very good and simple experiment you can do in your lab to study the Fermi energy of copper. Thanks for listening.